Today we're going to talk about the similarities between gravity and electric charge. So on the top of the screen we have gravity, and on the bottom we have the electric charge. And what I've drawn here is the source mass, which is in the middle, and the field lines for gravity all pointing in. That's because gravity is attractive, so the field lines are going in. On the bottom is a positive charge, the source charge, which is right here, using my pointer. And the field lines, by convention, is pointing outward. Because the positive charge, because it's positive, we've decided the convention is for positive charges, the field lines would point outward. So if this were a negative charge, the field lines would point inward, very similar to what gravity looks like. So let's look at the first similarity between gravity and electric charge. The first one is the force that the source mass provides to a test mass, if you will, that's located within the gravity field. And that force is, according to Isaac Newton, is a product of G, which is the gravitational constant, the source mass, the test mass, divided by the square of the distance between the centers of the source mass and the test mass. So that's the formulation for the force, according to Newton's gravitational law. Now, for Coulomb's law, it's a very similar picture. We have a constant, which is now the Coulomb constant, which is a product of, which is multiplied by the product of the source charge, the test charge, and divided by the square of the distance between the source and the test charge. So we have very similar formulation in the forces. Now, I'm going to move this mass from here to the bottom. So this becomes a force per unit mass, force divided by mass. And we have the expression Gm over r squared. And we know that this one is equal to what we call the acceleration due to gravity. And so rewriting this equation, force is equal to ma, which is Newton's second law. So if we substitute the values for the source mass, which is the mass of the Earth, which is 5.972 times 10 to the 24th kilograms. G is 6.67 times 10 to the minus 11 Newton meter squared per kilogram squared. And R is 6,378,000 meters. That's the distance from the center of the Earth to the surface of the Earth. And we get a value of 9.8 newtons per kilogram. That is also 9.8 meters per second squared. They're one and the same thing. So newtons per kilogram and meters per second squared are exactly the same thing. It's the force per unit mass, or it's the acceleration due to gravity, which is actually the electric field. So this is not the electric field, the gravity field. The strength of the gravity field is G. The mass, the test mass, is whatever mass you say. Let's say you're 100 kilograms. So if you're 100 kilograms, the force that the Earth exerts on you is 980 newtons. So now let's look at the bottom. The force is kq, large Q and little q divided by r squared, Coulomb's law. Now we substitute in the value for k, which is 8.99 times 10 to the 9th Newton meter squared per Coulomb squared. And I put this q on the bottom here. So it's going to be the force per charge. Now this quantity is called the electric field. It's just like G is the strength of the gravity field, E is the strength of the electrostatic field. So E is the force per unit charge. It's kq over r squared. So, which means that we can rewrite the force equation as the electric field times the test charge. So you have to remember this formulation for E, kq over r squared. Now let's look at the next thing, which is potential energy. On the top, of course, we have gravity, and we have gravitational potential energy. From the work energy theorem, the work is equal to force times the distance, and it will be equal to the potential energy, or the change in potential energy. We define potential energy is to be equal to zero at an infinite distance away from the source mass. That's how we define where potential energy is zero. Now we know from Newton's gravitational law that the force is gm times little m, big M times little m divided by d squared. I'm changing variables now to d because d is now the distance between infinity, and we're bringing it in to a distance d from the center of the source mass. So we're going from infinity to d. So this is the amount of work that is done to this charge. And why is it negative? Because we're not doing any work. We're letting gravity do the work. So when gravity does work, it's negative work because we're not working against gravity, we're working with gravity. So it becomes negative because the force is attractive. So remember, F is gmm over d squared, and we have distance on the numerator. So the square cancels with the d, so you're left with just one d on the bottom of the fraction, and the potential energy U sub g here is equal to minus g times the source mass times the test mass divided by the distance. So that is the potential energy. Now that's working with gravity. When you work against gravity, that means you're taking a mass from a distance that is, let's say, at the surface of the Earth to a higher distance from the center of the Earth. So this is positive, this is h, this is the surface of the Earth, and this is h. That potential energy is equal to the mass times the acceleration of gravity times h. That is now a positive potential energy because we're working against gravity. So this is negative potential energy from infinity to d. This is, let's call this d again, except this one where it's a delta d, a positive delta d. This is a delta d. So the potential energy, you're going against gravity, is a positive number. So that's how gravity works. Now with charges, it's the same thing. The work energy theorem, force times the distance is equal to electrostatic work. And we know that from Coulombs law, the force is kqq, large q and little q, divided by d squared, multiplied by a distance. And so the d's cancel. One set of d's cancel, and you're left with the electrostatic potential energy is equal to k times the source charge times the test charge divided by the distance d from the source charge. So that is an evaluation of the electrostatic potential energy. Now let's look at the next one. The next level is the gravitational potential. The gravitational potential is defined as the gravitational potential energy per unit mass. So let's temporarily put back the d here so that we have the d squared here. Now we recognize this term. as the acceleration due to gravity. So that's g, little g. That's the 9.8 meters per second squared that we're familiar with. And d is the distance from a reference plane to a higher distance if it's positive, and to a lower distance from the reference plane if it's negative. So if it's positive, that's like pumping water into a water tank, pumping it up. That's the distance d. Now we have now acquired a gravitational potential of the acceleration of gravity times d. That's the gravitational potential, which is just simply the height d above the reference plane. And if it was negative, it'll be negative. So that's gravitational potential. Now, electrical potential is very similar. It's the electrostatic potential energy per unit charge. Now we come up with a new symbol for it. We call that voltage. We know that potential energy is kQq over d, but since we're dividing per unit charge, the q's cancel, and we are left with this expression for the potential. It's kq, take out the d, take out the q, so it's just kq over d. That is the electrical potential or the electrostatic potential. The units are either joules per coulomb, or that's also defined as volts. 1 joule per coulomb is a volt. So this is joules, this is coulomb. So that's a joule per coulomb, and that is a volt. That is the definition of a volt, is joules per coulomb. So that brings us to potential. And that concludes the similarities between gravity and electrostatics. So this is all shown in your book on page 418. Page 418 in your book. And if the symbols are slightly different, that's because I chose it to be that way, hopefully trying to explain it a little bit better by having consistent units. But anyway, you can break it down on page 418 and you'll get the same type of derivation in the similarities between gravity and electrostatic charge. So in the slideshow, Unit 7, Electromagnetics, Part 2, slide number 18, there's a problem. And the problem, it's problem 1. The problem states a source charge of 20 microcoulombs is deposited at a point in space at coordinates in the xy plane. So that's the xy plane right there. What is the force felt by a unit positive charge at coordinates 3, 4? So that's 3 on the x-axis, 4 on the y-axis. So that's the location of the test charge. So the force is felt by the test charge. And it's a unit positive charge, so it's a Q equal to plus 1.6 e to the minus 19. And so the force is K, 8.99 e to the 9th times 20 e to the minus 6 and 1.6 e to the minus 19. And what is this distance? And recognize this is 3, 4, and that is a 3, 4, 5 right triangle. That's one of those right triangles where it happens to be a known value. If your sides are 3 and 4, then this hypotenuse is 5, so that R is now 5 squared, 5 meters. We're using, of course, the units for distance is meters. And so we just evaluate what that equation says, and that's what the answer is. And so the answer is the force is equal to 1.15 e to the minus 15 newtons. So that's part A. What is the electric field strength at coordinates 3 and 4, and how does it compare to 1.5-2? So 1.5-2 is actually half as much. So this length would be half. And the electric field strength, E, and that's a vector 2, is equal to KQ over R squared. And so that's 8.99 e to the ninth times 20 e to the minus 6 divided by 25. And so the solution to part B, which is the electric field, is 7,192 volts per meter. That's when you multiply this constant times 20 e to the minus 6, which is the charge, divided by the distance squared. And the part B also asks, what happens when you change this distance to half? That means that the strength will be 4 times as much, right? Inverse square. So the electric field will be 4 times 7,192 volts per meter. And it also asks whether the direction has changed, and the direction is still towards the minus charge, towards this center point on this coordinate system. Part C, what is the electrical potential energy that can be generated by this unit charge, and is this a scalar? And so the potential energy, and we call this symbol U sub E, is going to be KQQ over R. And so once you substitute the values, you get a number. That's, if you remember, one of the things we reviewed earlier as to what the formulas are for potential energy and potential. That's one of them. And the last one, what is the electrical potential, which is the voltage, is going to be KQ over R. So let's look at the last one first, D. That's 8.99 e to the ninth times 20 e to this minus 6 over 5. And that is going to be volts. So here are the results. The potential energy is 5.75 times 10 to the minus 14 joules. And the voltage is 359,600 volts. So this quantity is the same thing as the voltage times the charge. So if I multiply this by the charge, which is 1.6 times 10 to the minus 19th, if it's only 1 electron, it's a minuscule amount of energy. So that concludes problem number 1. So problem 2 is about these 2 steel balls that are in a that are charged such that when they are charged with negative charges on each one, they repel in such a way that the included angle is 60 degrees here, which makes this an equilateral triangle, 20 centimeters, 20 centimeters, and 20 centimeters. So that's given in the problem. The string length is 20 centimeters, and the included angle from the repulsion force is 60 degrees between the two strings. And so the question asks, how much charge is deposited on the steel balls? And this is a combined Newtonian mechanics problem and an electrostatics problem, because there's going to be tension in this string, they call it T, and there's going to be tension T here, and those tensions are going to be equal. And the vertical component of this tension is going to be equal to the weight of the steel balls, and the horizontal component will equal each other, and they're going to be opposite each other, and they will be what will give you the force. And the geometry drives the magnitude of the force. So what does the geometry tell us? So the geometry tells us that this is going to be, that this horizontal force is going to be mass times acceleration of gravity times the sine of 30 degrees, which is the half angle between the two of them. And that is going to be a force in newtons. So this is equal to 0.016 kilograms times 9.8 meters per second squared times the sine of 30, which is 1/2. And that gives us a force that is equal to 0.0784 newtons. And the separation distance is, now we know, is 20 centimeters. And so this force now is equal to K Q squared, because there's two charges that are going to be equal and opposite, and divided by over r squared. So when you solve this problem, you get a number of the charge is the only unknown, is equal to 5.9 times 10 to the minus 7th coulombs. And if you want to find out how many electrons that is, you divide it by the charge of an electron, which is 1.6 e to the minus 19, and you get the number of electrons, which is 3.69 times 10 to the 12th, so 3.9 trillion electrons. 3.69 trillion electrons is the answer. Problem 3 is asking, why can't electric field lines ever cross? Or do they cross? And the answer is no, they can't cross, because they can't possibly cross. Each point in space is represented by a single vector. And so if the lines cross, that means that this vector is no longer focused on this charge, and that's not a possibility. If there's only a single charge, they all have to be focused on that single charge. If there's another charge, it'll alter the electric field. Still, they won't cross, because it alters the electric field in such a way that there's still only one unique vector for every point in space that is defined by that field.